Yeah. A pleasant evening to everyone, and very good morning to Professor Mary Frecker. Uh, Professor Mary Frecker is a professor of mechanical engineering and biomedical engineering, the Leighton Rice Chair in Engineering, and the founding director of the Center for Biodevices at Pennsylvania State University. She has served as Associate Department Head for Graduate Programs in Mechanical and Nuclear Engineering and also as the Director of the Bernard Gordon Learning Factory in the College of Engineering. Dr. Frecker has a BS from the University of Dayton and an MS and PhD in Mechanical Engineering from the University of Michigan. Upon joining Penn State in 1997, she was awarded the Pierce Endowed Development Professorship in Mechanical Engineering. She has also been awarded the prestigious GM Fredenston Young Investigator Award by the American Society of Mechanical Engineers Mechanism Committee in the year 2002, followed by the Outstanding Advising Award by the Penn State Engineering Society in the same year. And also she has got the Outstanding Research Award by the Penn State Engineering Society in the year 2005 and also three ASME Best Paper Awards in the year between 2009 and 2015. She served as an executive leadership in the Academic Technology and Engineering Elite Fellow in 2018 to 2019 and completed the Changing the Future for Senior Women Faculty in STEM Leadership Program in the year 2019. She is a fellow of ASME, is currently chair-elect of ASME Mechanisms and Robotics Technical Committee, and has served as an associate editor of the ASME Journal of Mechanical Design, chair of ASME Adaptive Structures and Material Systems Technical Committee, and executive committee member of the ASME Aerospace Division. On behalf of IEEE, I request Professor Mary Frecker to kindly present her talk, and the stage is yours, ma'am. Yeah.
Okay, thank you very much for that nice introduction, and thank you very much for the invitation to speak with all of you today. It's very nice to be here. So I'm Mary Frecker from Penn State. My research group is called EDOG, which is the Engineering Design Optimization Group Lab, and that's my dog. So I'm going to talk today about some of our work in optimal design of adaptive structures, particularly self-folding origami and metamaterials. So let's begin with origami. So origami is the ancient Japanese art of paper folding. Many of us have probably folded this paper origami crane ourselves. Origami comes from the Japanese words ori, which means fold, and kami, which means paper. What we're interested in is what's called origami engineering. So in origami engineering, we're interested in using engineering materials instead of paper, but using this idea of folding to achieve large shape changes or deployment. So some very practical examples of origami engineering are pictured here. So one is this coronary artery stent, which is folded down into a very small and compact shape for insertion through a catheter. Then it is deployed, it's in this case inflated with a balloon, into a much larger shape to remain in place. Another example is the automotive airbag that many of us have in our cars. So the fabric of the airbag is folded using a very particular origami pattern so that it's folded so that when it is stowed, it will, when it is needed, deploy in a very precise and reliable manner. So parachutes operate using the same principle. The parachute is folded using a very particular folding pattern so that the parachute will deploy very reliably when it is needed. So one of the aspects of origami is what's called self-folding origami. And recently, researchers in fields like compliant mechanism design and smart materials and even the visual arts are collaborating on developing self-folding origami concepts and technologies. So in the top picture there is a walking robot that was developed by the MIT Harvard group. So it starts off as a flat sheet and then uses shape memory polymers to fold up into this 3D shape. So you can see the legs of the walking robot. And then there's a separate servo motor that provides the power for walking. In the bottom is another example of self-folding origami. In this case, this is a soft material, and we achieve actuation. In this case, this material is called Shrinky Dink, which is being used by a group at NC State. And we see with these soft materials, we achieve sort of curves and kind of localized bending as opposed to very sharp creases like we would see with rigid panels or with paper. But again, the idea is that we can fold up or unfold to achieve some kind of large shape change. An application of origami and self-folding is this star shade, which is currently being developed by NASA's Jet Propulsion Laboratory. So the star shade is folded into a very small and compact shape for launch. And then once it's up in space, it's deployed into this much larger shape, and it acts as an optical shield. And the shield blocks the light from a distant star, and the exoplanet telescope is able to study the planets orbiting the star, as is pictured in the video here. So we collaborated with JPL on this project and developed a simulation of this optical shield using a particular origami pattern, which is called the flasher pattern. And you can see here the large shape change that is obtained. The diameter of this optical shield when it's stowed or folded up for launch is 3 meters. And when it's fully deployed, it's 20 meters. If we include the petals that were around the circumference there, the total diameter is 34 meters. So we did this multi-body dynamic simulation using Adams software and showed that we were able to achieve full deployment or unfolding using this particular crease pattern. This is work done by one of my former PhD students, Landon Bowen. So here's some of the results from our simulation. If we look at one sector of this flasher pattern, we triangulated each one of the rectangular rigid panels. So all of the panels in the sector are triangulated, so each rectangular panel consists of 2 triangular rigid panels, and there's a joint in between. So the joint rotations of these intra-panel joints are pictured here, and the numbers just indicate the joint numbers. Oh, sorry if you can hear my dog in the background. And we can see that as we begin to open or unfold this star shade, some of these intra-panel joints experience quite a bit of rotation, even up to 40 degrees. So what this tells us is that we cannot use perfectly rigid panels. We need to have significant flexibility. This triangulation is approximating the flexibility in the panels. So one of the questions then in self-folding origami is, how do we actuate the folding? And I wanted to highlight some of the work being done by two of my collaborators at Penn State. Paris von Locket's group is developing these magnetoactive elastomer materials that respond to magnetic field. So the magnetoactive elastomer consists of hard magnetic particles in an elastomer matrix, and the material is pulled with a high magnetic field so that it has a preferred orientation in the field. So when a magnetic field is applied, as is pictured in the video here, the material wants to rotate to align with the magnetic field, and we can leverage that to achieve folding. We also are looking at electric field actuated materials, and Zubeida Oneas's group is developing these electrostrictive PVDF-based terpolymer materials. So these are what's called EAPs, electroactive polymers. And when we apply compliant electrodes on a thin sheet of this polymer and apply a voltage across the material, the electric field causes the material to stretch. And I can convert that stretching into bending by bonding the active material to a passive material substrate. And I can localize that bending into folding by cleverly designing the substrate, which I'll talk more about in a moment. So one of the things we're interested in is multi-field actuation. So using both this electroactive and magnetoactive materials in the same structure. So a simple example is pictured here, which is a bimorph. So you can see the terpolymer layer in orange there, a passive substrate. In this case, we're using Scotch tape, and patches of this MAE material. So here we're introducing a notch in between the two pieces of the MAE material. That notch acts to localize the bending into folding. So some of the results are shown here, and this is work done by my former PhD student, Wei Zhang. The actuation of the MAE is pictured in these top two rows. So at zero magnetic field, we have zero deformation. As I increase the magnetic field going to the right there, you can see increased deformation and this localized bending response. We use these experiments then to validate finite element analysis models of this bimorph structure, which you can see we achieved good agreement. And then similarly, I take the same bimorph structure and apply the electric field. So here I get bending response in the opposite direction. And I do get that localized bending, something more like folding as opposed to uniform curvature with the electric field actuation of that terpolymer material. So as I increase my electric field, I get increased response. And again, we're getting good agreement between our finite element predictions and our experimental measurements. So one of the questions then in designing these multi-field actuated structures and self-folding origami is where should the active material be located? How much of it do we need? What should its orientation be? What should the geometry of the passive material be? And in order to answer those questions, we have developed this two-stage optimization procedure. So stage one uses low fidelity models like an analytical or a pseudo-rigid body or a rigid body dynamic model to approximate the effect of the active materials on the shape change. And here we're using the optimizer called NSGA2. This is the non-dominated sorting genetic algorithm, which is available through MATLAB. This is a multi-objective GA that is well suited for problems with more than one objective function and a relatively small number of variables like we have here. So we do this stage 1 optimization using low fidelity model, and then we take the best design from stage 1 and use it to seed the initial population in stage 2. We convert the low fidelity model to a continuum model and use a full multi-physics finite element analysis here, and again use the NSGA2. So we're using this stage 2 really to do kind of fine-tuning of the result that we came up with very quickly with the low fidelity models in stage 1. So let me illustrate this 2-stage approach first with an example of a notched unimorph structure using the terpolymer material. So we have a layer of terpolymer and then some notches introduced in the passive material. We're interested in what's the best width and location of those notches, the thickness of both materials. And the motivation for this this particular problem is shown in the bottom right here, where you can see I have a notched terpolymer unimorph here. When I actuate it, I get this very large deformation. Our idea here was that we could use this type of structure as a finger in an active gripper. So I could use 3 of them, for example, to achieve a stable grasp. So let me walk you through the application of this 2-stage procedure to this particular problem. So in this case, we're considering 2 objective functions. If you think about this idea of the gripper, I want to maximize what's called the free deflection. So that's this delta free. And that will allow a large grasping motion of my gripper. So the free deflection is the deflection upon actuation with nothing resisting the structure, and that represents the maximum deflection that we could ever achieve. At the same time, I want to also be sure that my structure can impart sufficient force. So we're using this FB, or what's called the blocked force. So if I block the tip and impose that 0 deflection condition, the reaction force obtained is called the block force, and that's the maximum force that we can ever achieve. So I would like to maximize both of those things, and I can accomplish that by minimizing their negative. The variables in this case are the geometry of the terpolymer and the substrate, as I mentioned, the thicknesses and the lengths of those different segments. So here's what the result looks like. This is what's called a performance space plot. So the X and Y axes are my objectives. So I have a normalized measure of the free deflection on the X and a normalized measure of the blocked force on the Y. So you can see the set of blue points here is the Pareto set. So for multi-objective problem, I get a set of solutions, not a single design. And this is the final generation. Here, I should mention the low fidelity model that we're using in conjunction with the GA is an analytical model. So it's based on beam theory. And the best design in this performance space plot is one in the lower left-hand corner of the plot. So one that has very high free deflection and block force. But there are no designs in the lower left-hand corner. So as a designer, you choose which design is best based on suitable trade-off between the two competing objectives. So here we've chosen, just as a basis for comparison, a standard unimorph. So just a uniform thickness polymer sheet bonded to a uniform thickness substrate. And our best design, in this case, we're choosing to select that design based on the minimum distance to what's called the utopia point. So the utopia point would be the origin in this particular example. So the design with the minimum U, that distance measure is pictured here, and then two others just for basis of comparison. So you can see the standard, the free deflection and blocked force provided by the standard unimorph, and we've used the same volume of terpolymer material for, I'm getting some feedback, sorry about that. The best design, the volume of the terpolymer material we've set to be the same. We've set this volume of the standard unimorph to be the same. So if you compare then the bottom row and the top row here, you can see for the same volume of active material, I get much more blocked force in my best design, and sacrificing a little bit in the free deflection. Design 1 and design 2 there, you can, just for comparison purposes, you can use those to kind of get an idea of the trade-off between the free deflection and blocked force. I'm sorry, just could I ask everyone to mute their microphone, because I'm getting a lot of background noise and feedback. Thank you. So I take that best design from stage 1 and use it to seed the initial population in stage 2. So in stage 2, here we're using the full finite element analysis in conjunction with the NSGA2. So here's my results in stage 2, same performance space plot. Here's my Pareto set. And my best design I've selected again as the one with this minimum distance measure U. And you can see this tapered design from stage 1. I've introduced now in stage 2 some new variables that allow these segments to not only change in thickness and length, but also to change in slope. So I can get some kind of tapering in the segments. And here's what my results look like. If I compare again to that standard unimorph, I was able to, in going to stage 1, to get almost 21% improvement in blocked force with about 9% reduction in free deflection. Then compared to the best design in stage 2, for no change in the free deflection, just by adjusting these slopes of my segments, I can get a 30% increase in my blocked force. So I can increase my blocked force without sacrificing anything in my free deflection. So let me go through another example here. In this case, we're considering multi-field actuation. So the inspiration for this problem came from this sort of origami-inspired coffee table, which has this crease sort of down the center. And for this particular problem, we'd like to have the corners fold in, shown in the red there, due to application of the electric field. And then we'd like to have that big fold down the center, shown in the green. We'd like to have that happen when we apply the magnetic field. And then when I apply both fields simultaneously, I get both of those at the same time, as shown in the blue. So here's what our two-stage design process looks like for this particular problem. In this case, I'm using a rigid body dynamic model in stage 1, and then I'll take the best design from stage 1 and use that to seed my initial population in stage 2, where I use the higher fidelity finite element analysis. In this case, I have 2 objectives. The first one is to minimize the shape error. So we're parameterizing shape error using a number of control points on the surface of my structure. And when I apply the field, I get some deformed shape of my structure, and the desired position of all of those control points represents my desired actuated shape. The difference between the actuated shape that I get and this actuated shape that I want represents my shape error. So I actually have 2 measures of shape error, one due to the electric field, one due to the magnetic field, and I add those together to get the total shape error. The other objective that I'm considering here is just the total amount of the active material. We would like to minimize both of those. So in this case, we start stage 1. The first thing we need to do is determine the crease pattern. So we're doing that using a software called Origami Pattern Designer, which was developed by our collaborators. That tells us where the creases should be. And then we formulate our design problem. So our 2 objectives here, as I mentioned, are the shape error, that's psi, and we're approximating the total amount of active material using the torque applied by the active materials. So the reason we're doing that is using this rigid body dynamic modeling approach, as shown in the bottom here. We have rigid panels that are connected by torsional springs. The torsional springs represent the stiffness of the creases. The torques represent the effect of the active material. And this rigid body dynamic model is very amenable to this application of externally applied torques. So I have torques applied due to my magnetic material and to my EAP material. So my variables in this case are the values of those torques and the stiffness, the spring constants of those torsional springs. So I take that result then from stage 1, I take it to stage 2. Here's what the problem looks like for stage 2. In this case, for this coffee table example, my magnetic and electric field induced actuations are completely independent of one another. So we can decouple the high fidelity FEA, which helps speed things up because I can do those in parallel. So for the magnetic field actuation shown here, my 2 objectives are the shape error, that's epsilon, and the V total, that's the volume of the active material. Again, my variables are the geometric parameters that define the magnetic material and the crease material. And I have a constraint on the crease stiffness, which comes from that stage 1K, that torsional spring stiffness. Now, one other thing that I need to consider here in the modeling of this MAE material is the fact that as the magnetic field is applied, my structure is changing orientation in the field. So the torque, the effective torque of due to the magnetic field is this M cross H term. And I can account for the fact that the relative orientation between the magnetization M and the applied field H are changing using this unit normal vector N and the angle alpha. So that's what's pictured here, that allows me to account for that orientation. So then the other piece of stage 2 is this electric field induced actuation, so due to the terpolymer material. So in this case, my two objectives are the same. I have my shape error, which is psi, and my total volume of the terpolymer material. My variables are the geometric parameters defining the terpolymer increased material. In this case, we're applying a strip of the terpolymer across the crease at those corner tabs. This sort of high aspect ratio configuration of the terpolymer will achieve the most bending, or the most folding in this case. So here's what the results look like. From stage 1, I have my performance pace plot, as we had, similar to what we have seen before. This is using my rigid body dynamic model now. The best design in stage 1, we're selecting as the one with the minimum shape error as shown here. And we'd like to take this design, convert it to a continuum model for stage 2, and then use stage 2 to further improve the shape error. So here's what the results of stage 2 look like. This is for the MAE, or the magnetic field induced actuation. The baseline design, so the design from stage 1, is pictured in the blue triangle there, and then my Pareto points are the red dots. In this case, you can see that we can improve the shape error quite a bit compared to the baseline design, but we can only do that by using more volume of active material. Every design there has more volume than the baseline design. And this is what the best design looks like. This is the one with that minimum U again, and the actuated shape is very close to what we had specified as our desired shape. For the terpolymer, again, you can see the baseline design there compared to the Pareto points. The best design is also selected as the one with the minimum U, that distance measure. And my deformed shape is pictured here, which again is giving us much lower shape error. So we can see that numerically here. If I look at the baseline design in the MAE case, you can see this large improvement going from 1 to 0.3 for the best design in the MAE. And I do that at the expense of having to add a bit of volume of active material. Similarly, for the terpolymer, if you look at these last 2 rows here, the baseline design, I improve the shape error from 0.4 to 0.3, but at the expense of adding volume of terpolymer material. So in this case, in both cases here, I'm getting a big improvement in shape error for a modest increase in the amount of active material. So one of the reasons for, or the sort of motivations for developing this 2-stage design process was to help address this trade-off between accuracy and computational efficiency. So if we look at the model, the analytical model that we used for the terpolymer gripper compared to the high fidelity finite element model, you can see here we're measuring the inverse of the computation time, using that as a measure of the efficiency. As you would expect, the low fidelity analytical model is much more efficient than the finite element model, but is not as accurate. The finite element model is much less efficient, but is extremely accurate. And in this case, we have experimental data to compare to. So our stage 1 optimization, in this case, the whole genetic algorithm converged in 130 seconds using this analytical model. If I would have used the same initial population, the same number of generations, using the finite element model, we're estimating that it would have taken 104 days to solve the same problem. So this sort of illustrates the benefit of using that low fidelity model to quickly come up with a pretty good solution that we can then fine tune with the high fidelity one. And then similarly for the coffee table example, here we have a rigid body model compared to the finite element model. The lower fidelity rigid body model is much faster, but not as accurate, whereas the finite element model is much slower, but is much more accurate. So in this case, the stage 1, the entire GA converged in 24 hours using the rigid body model. And we estimate that it would take 60 days using the finite element analysis. The total computing time for stage 1 and stage 2 for this example was 9 days, which isn't very fast. However, we're estimating if it would have, the entire process would have been done using the finite element analysis, the high fidelity model, it would have taken 10 times that amount of time to solve, or 3 months, 90 days. So I want to move on here to talking about some of the work in metamaterials. So these origami-inspired structures are also being used in the context of metamaterials, where sort of repeated units of these origami structures or tessellations are being used. And Howell's lab at BYU has looked into these, and other groups as well. And even kirigami, which is origami with cuts in it, are being investigated for metamaterials. In all these cases, the idea is we can design the unit cell so that we achieve some effective material behavior of the entire metamaterial. So one of the things we've been looking at is using what's called contact-aided compliant mechanisms. So contact-aided compliant mechanisms were initially investigated by my colleague Suresh almost 2 decades ago. And a contact-aided compliant mechanism has some surface that comes into contact either with itself or with an external surface during the motion of the mechanism. We've been looking at using cellular arrays of these things where we have self-contact. So you can see in both of these videos of these sort of cellular arrays, the contact surfaces come into contact as I stretch the array. Now, one of the reasons to use these is because when that contact happens, I get an effect called stress relief. So the contact adds an additional load path in the structure. When that happens, it causes the stresses to redistribute. And I actually can reduce the peak stresses, and in these cases, stretch my array farther than I could with the same cells without contact. So we were looking at these for applications like morphing aircraft skin. Recently, thanks to progress in additive manufacturing, and in particular metal additive manufacturing, we've now been able to consider 3D versions of these contact-aided compliant mechanisms. And we're actually calling them C3M, or contact-aided cellular compliant mechanisms. And with modern, metal 3D printers, we can print very thin walls and intricate contact surfaces like we would need for these C3M structures. The one pictured here was printed at Penn State from Inconel, which is a nickel-based alloy using a powder bed fusion process. So we're envisioning something like a sandwich panel of these 3D C3M cells to be used in applications that would require energy absorption, like sports equipment or vehicle armor. So if we look at the unit cell design, then the question is, how do we design these unit cells for both energy absorption and AM processing? So one of the areas that we've looked into in the context of these C3M metamaterials, and this is work done by Jovana Jovanova, who was a postdoc working in my group. If I look at the unit cell of this three-dimensional C3M structure, I can incorporate superelastic nitinol, use that as the material to take advantage of the superelasticity. So this is nice for compliant mechanisms because I get highly compliant, flexible structure that is still elastic. So all of the strains are recoverable. Excuse me. I can also take advantage then of the contact, and further, I can take advantage of the functional grading to tailor my behavior. So here's what this might look like. In this plot, I have on the x-axis the maximum stress observed in the structure, and the max stress happens in these curved walls, and the amount of energy absorbed by the unit cell. So as I compress the cell, I can compare using a superelastic nitinol structure to one with just a linear elastic material with the same initial modulus. As I compress the cell, my maximum stress increases, as you would expect. But when that phase transformation happens at the onset of superelasticity, I get a big change in slope. So that's that blue triangle near the bottom there. And as I continue to compress the cell, it continues to increase. The energy continues to increase. And the blue dot indicates the onset of contact. So I get another change in slope at the onset of contact. If I continue then to compress the cell, my maximum stress continues to increase. If I set my stress limit at the end of that superelastic region and compare then, that's the vertical line, compare the energy absorbed of the superelastic cell compared to the linear elastic cell, you can see that much more energy is absorbed. And I can also get this very nonlinear stiffness behavior. So I'll talk about how we achieve this in a couple of slides, but I want to talk more about the functional grading first. So we had this idea to be able to achieve, very nonlinear tailorable stiffness by varying the superelastic response in those highly compliant regions. So in this case, we're looking at three different materials, A, B, and C, as are pictured in the lower right-hand corner. You can see the superelastic response. So all three of those have a different onset of superelasticity and a different effective modulus. And we looked at different combinations of these materials. We're approximating functional grading then as step changes in these different materials. So in the big plot then, you can see as I compress the cells, the maximum stress and the energy absorbed increase. I get this big change in slope at the onset of superelasticity. I get another change in slope when contact happens, and then another one when we've reached the end of that superelastic region. So again, here I can choose a combination of materials to maximize the energy absorbed, or I could choose some combination of materials to get some desired nonlinear stiffness behavior that I would like. So this is completely sort of tailorable for whatever the needs are for the application. So how do we achieve these different materials? One of the projects that my collaborators are doing at Penn State is looking at developing a direct energy deposition process. So this is an additive manufacturing process that it's a powder fed process. So I can feed in my nickel and titanium powders, direct a laser at the powder stream, and create a melt pool. And this is a video of this process happening. This is nickel titanium powder. We can adjust the elemental composition of the powder. So the blend of nickel and titanium, atomic percent nickel versus atomic percent titanium, to tailor the superelastic properties. So this is ongoing work happening right now at Penn State in collaboration with a local company called Nittany Laser. So one last application that I thought this group might be interested in. We're also looking at applying this idea of being able to additively manufacture the functionally graded nickel titanium to a medical device application. And the application is stents that are used in the GI tract. So esophageal stents are currently used in off-label procedures where they're put in place to repair leaks, for example, as is shown in the upper right here. But one of the problems with this type of treatment is that the stents are often put into place into curved regions of the GI tract. And when the stent is placed in a curved region, it doesn't want to remain curved. It wants to return to its neutral state, which is a straight position. And what happens with that is that the stent tends to what's called migrate or move in the GI tract. So we were looking at solving this problem by designing a stent that would be very easy to bend and less likely to migrate. And with the ability to use additive manufacturing to fabricate complex 3D shapes with functional grading, we can actually consider fabricating some of these types of designs. So in this case, we're assuming two different materials that are shown in the blue and the orange here. The blue material would be used in the center or narrower region, and the other material in the other regions. We looked at these different sort of hourglass designs, which I'll talk more about in a second. So here we're approximating functional grading using two different materials. And this is one of our examples of an actual printed nickel titanium helical stent, and you can see the scale there with material with higher compliance in the center region there. So we set up an optimization problem. In this case, we have two objectives. We want to minimize the bending moment needed to achieve a 90-degree bend, and also the bending stiffness. And the variables are shown here, which here we're using a helical stent. So some of the helix parameters, like the pitch, are used as variables. The LS is the length of the span of that section of lower compliance material. We have a stress constraint, and this lambda is the stretch, which is correlated, so the stretch in the helical strut, which is correlated to buckling. So by putting an upper limit on the stretch, we can prevent designs that would buckle. So we've looked at n = 1, 2, and 3 narrow regions, and I'll show some more details on the next slide. One thing to notice here is all three of these are able to achieve this 90-degree bend by and satisfying all the constraints. You can see there is a difference. If, for example, the n equal to 3 design, we see changes in diameter of the helical stent as I bend it, whereas the n equal to 1 design, which doesn't have really that narrow region, tends to maintain a more constant diameter, and 2 is somewhere in the middle. Here, I should mention we're using the NSGA2, the same optimizer that I mentioned earlier, and we're using COMSOL FEA to model the superelasticity. So here's some of the results. For n equals 2 and 3, the bending stiffness and bending moment are pictured here. One thing you can see, especially in the n equal to 3 design, due to the complex relationships between the different parameters in this problem, there's not a one-to-one relationship between the bending moment and bending stiffness. And the best designs are noted with the star. Those are design A's, and those are the ones that are closest to the utopia point, like we saw before, and then some other sample designs here. So that helps a designer, or in this case, a physician, select an appropriate design based on their requirements for the problem. So if a design with lowest bending moment is important, then design B might be chosen, or on the left, design B. In any case, the designer or physician can use these type of results to select an appropriate stent for a particular patient or a particular condition. Okay, I just want to wrap up here and summarize. I talked about several different applications and optimal design approaches for problems like self-folding origami, C3M metamaterials, and superelastic nitinol stents. I'd like to conclude just by posing some ideas here, and maybe this is something we can bring up in the discussion. There are many challenging research problems in this area, and many problems that I think would be helpful for all of us to consider collaborating on. So, for example, as we look at adaptive structures and different types of active materials, we need to consider multi-physics type of analyses. So electro, magneto, thermo, mechanical, and maybe chemical, for example. Material, geometric, and other nonlinearities need to be taken into account for things like very soft materials, very large deformations, buckling type of behavior, and other things. And then as we look into additive manufacturing, things like fabrication process simulations also become very important to the design. So, for example, in the figure pictured here, there are tools now that can predict thermal distortion as we print using a laser-based process. And there are many sources of variability that come up in these additive manufacturing processes that are only just beginning to be understood. And how do we incorporate those into a robust design approach? So all of these complex, computationally intense analyses really require us to look at more efficient algorithms and optimization strategies. And I think machine learning is a promising approach that we and other research groups too are beginning to look into. So I'd like to end by acknowledging the contributions of my students and my collaborators, and also the funding agencies who have supported this work, and I will be happy to answer any questions. Thank you.
Thank you, Professor Mary. I think we have a sufficient time for questions as well. So some of the audience members have posted their questions in the chat window.
Oh, okay.
So you can also have a look. Are you able to view it?
Yes, I'm seeing it now. Okay. So Dr. Palani is asking, what is your comment on the life cycle behavior of the bimorph? That is a really good question. You know, we have not evaluated that quantitatively. One of the challenges, so particularly with the terpolymer material, is you know, we need a very sort of uniform surface with the electrodes, and my collaborators are, you know, working on that. The electrodes must be compliant, but also very uniform. So if there are any defects in there, you know, they can sort of start to accumulate and cause shorts, which causes the you know, can cause the device to fail. So I think probably for the bimorph, that you know, sort of reliable, robust electrode design is probably the most critical part to achieving sort of a long life cycle. So another question. Oh, Suresh posted a link. You can make the NASA shield with paper on your own if you visit this website. So you can check that out. Thank you for that. So Ramachanda Krishnaswamy posted a few questions here. Are we comfortable today in combining high strain rate effects and large deformation for simulation and optimization? Yeah, that's a good question. I think, you know, we have addressed the large deformation. We haven't really looked at the high strain rate. So I'm assuming that this is related to the idea of energy absorption and impact absorption. Of course, there are researchers looking at that, and there are robust simulations. It's the same kind of challenge with optimization. It just, you know, is computationally intense, which makes the optimization take longer. Next question was, are there any rigid joints in the Flasher device that were adopted? So in the actual Starshade, what JPL was looking at was not using rigid joints. They were using actually a Kapton, which is a very sort of flexible polymer. So the panels were some kind of foam material that were adhered to a sheet of Kapton, and the Kapton acts as the compliant joints. Does the shield, once deployed in space, retract back to its original shape? Is there a need for this function? Yeah, I think the whole structure is designed to be able to actuate both ways. What they were using to actuate it was sort of a cable-driven system, so a motor to sort of you know, tighten or release the cables. So another question, Preeta Nair asks, are delaminations of the layers observed under large deformations? That's a good question. You know, one of the things that is, I didn't really get into this, but a common practice in the manufacture of these electroactive polymer actuators is to use multi-layer, and that allows the driving voltages to be lower when the layers are thin. So, you know, the more layers that are included there, sort of the more likelihood that, you know, things can delaminate. I have not seen a lot of problems with that. You know, there's glue that's used, but rather, instead of delamination, there can be problems where shorts sort of or on the edge of the material from one layer, so charge can jump across from one layer to the other on the edge. So things have to be, there's sort of a border of passive material that's left around the edge of each layer to help avoid that. Okay, Sudip Day asks, if there is panel deformation in a flash or origami pattern, it is not purely a mechanism anymore. Yes. How can it be analyzed as a compliant mechanism in that case unless a proper structural analysis is involved like FEM? Yes. So I think you bring up a great point. I think, you know, one of the purposes of that multi-body dynamics simulation that we did was to determine if the crease pattern made sense and how much panel flexibility would be needed. But in terms of, you know, the actual force needed to deploy it and how much strain is going to be encountered in those joints, you know, that kind of simulation would require a finite element analysis or something else, as you pointed out. Okay, so Gautam Kasturi asks, are these types of robots useful for space research? I don't know if Gautam could elaborate on that question. I'm not sure what these types of robots he or she is referring to.
Maybe Gautam, you can unmute your mic and ask the question if you're still there.
If not, maybe we can come back to that one.
Yeah, you can move on, Mary. Yeah.
Okay. Okay. Maybe he's referring to the gripper. Anyway, let me go on to the next one. There's still a few questions here. Viluri Sudakar asks, can we use the compliant mechanisms in any aircraft applications, mainly for vibration reductions? What about its performance over temperature? Yeah, that's a great question. So, you know, compliant mechanisms have been looked at for a number of years now for different morphing aircraft wing applications. It's been more in the context of achieving large shape change as opposed to vibration reduction. They have been, and my group did a project a few years ago looking at using compliant mechanisms with piezoceramic actuators in helicopter rotor blades. And the idea there was to, you know, deploy these actuated compliant mechanisms along the length of the rotor blade inside the spars to achieve camber change. And that is effective for vibration and noise reduction in a helicopter. Performance over temperature, that is a really good question. We haven't looked at that. For space applications, it's really important because there are really, really large fluctuations in temperature in you know, satellites, for example, depending on their orientation relative to the sun. So that is a great question. So Sahana asks, in the case of esophageal stents, n equal 2 and 3, according to the plot, it's mentioned that A is the best design. Since the best design is based on the requirements, why is A the best design? Yeah, that's a good question. So again, you know, for these multi-objective problems, we get a set of best designs, and those are the Pareto optimal designs. And then the designer has to choose some metric for selecting the one best design. So that metric might be, you know, if there's some minimum threshold in one of the objectives, we could use that. In this case, we chose the minimum distance to the utopia point as the metric, but that doesn't have to be the metric. Other measures could be used. So best is really only based on the metric that the designer chooses. All the designs in a Pareto set are best. And finally, Yash Agarwal asks, on slide 23, in metal additive manufacturing, is the design self-supporting? Is it geometrically accurate in the interior regions? What complications were faced in the manufacturing? Yeah, great question. Maybe I can go back here. There we go. Yeah. So in this problem, yes, all of the designs were self-supporting, and that's a big you know, consideration. Particularly using the metal additive manufacturing, where sometimes removal of the support structures is not trivial, and when you get into structures like this that have kind of thin walls, manually removing the support structures can damage the main structure. So yes, we want to avoid support structures. Just remind myself, what else was the question? Is it geometrically accurate in the interior regions? Yeah, that's a good question too. I guess it depends on you know, how accurate it needs to be. There is surface roughness with these powder-based processes. So that can be an issue, particularly when we're looking at contact surfaces. You know, in our analyses, we assume that all the contact surfaces are perfectly smooth. And if that surface roughness is big enough and the contact, you know, features are small enough, then it can interfere with that performance. And the last part was what complications were faced. Yeah, so surface roughness is one effect. The thermal distortion, I alluded to that on the last slide, but you know, there is work going on designing structures to be robust to thermal distortion. We did not account for that directly in this particular design, but I think that's a really important area, and will continue to, you know, develop. A few more questions. Dr. Ramesh Gupta asks, could you please suggest efficient origami models that can be used for solar panels deployment in space? So there are free, sort of freeware type of origami simulation softwares out there. So Tomohiro Tachi, it's T-A-C-H-I, who is a Japanese researcher. He has a software called Origamizer that you might check out. So, you know, these softwares are based, they're purely kinematic models. So they are typically, you know, assuming perfect joints, no thickness on the panels, and so forth. But, you know, for many origami structures, that's, you know, a pretty good assumption. So that might be one that you could check out is it's called Origamizer, and Tachi is the researcher. Okay, so Suresh asks, given the complexity of the design problem, you have used GA because of 2 objectives, I guess. Yes. The Pareto curves are slightly non-convex in most cases. Is there an insight here? Also, for n equal to 3, the Pareto curve was not apparent, one of the last slides. Okay. So in some cases, if there's only 2 objectives and they are entirely conflicting, you would expect this nice sort of convex Pareto set. But we don't always get that. Sometimes it's because we have another objective or constraints that are, you know, the removing infeasible designs that might otherwise fall on that nice convex Pareto set. So I think what you're seeing there is there are other factors besides those 2 that are competing, but in a 2D plot, we're only seeing 2. That was one reason we kind of tried to use the color in some of the plots. Maybe I can show an example of what, so for example, here, yeah, in this n equal to 3 design, we don't get, yeah, we don't get anything like a, that looks like a
Pareto curve.
Convex Pareto set. And I think it's because of these other factors like the buckling and stress constraints.
Yeah, thank you.
Mm-hmm. Okay, I'm seeing one more question. How useful for vehicle armor, slide 24? Yeah, that's a good question. Sorry, Natarajan Venkat asked, how useful is this for vehicle armor? You know, I think we don't completely know the answer to that. You know, one of the issues with vehicle armor is, you know, protecting from blast. So the Army, the US Army, for example, is interested in protecting the undersides of vehicles from what they call IED blasts. Another issue is also thermal, though, and that's something that I didn't talk about here, but what can happen is if we attach, you know, very sort of heavy metal plates to the underside of a vehicle, it can trap heat, which is, you know, can help damage the vehicle in a, you know, warm or hot environment, but also increases the thermal signature of the vehicle. So I think in order to really understand that problem, we need to consider both the sort of blast protection and the thermal aspects. So that's something that's, you know, still an open question.
What's the thickness you have achieved? What is the thickness?
Thickness of?
The structure for vehicle protection.
So the Army uses right now, they use just thick metal plates, so a few inches in thickness. Just solid metal plates are being used.
In the present case, in your design, what will be the thickness? Will it be more or will it be less?
Well, it can be tailored. So if we look at, we can manufacture cells, you know, that are definitely in that range. So you can see the scale here, the 12 millimeter scale bar there. We can manufacture cells that are, you know, small enough to do multiple layers to reach that type of thickness, or big enough to do small number of layers. That's doable.
Okay. Thank you.
Thank you very much, Professor Mary. I think you've taken a lot of time to answer our questions. I'd like to call upon Dr. Veda to make a few announcements.
Professor Mary, I would like to thank you. I'm Veda here. I'm the secretary of IEEE. On behalf of IEEE and the entire audience, I would like to thank you. It's been a great opportunity for us to listen to you and look at the new revolution that is happening in the area that you're working, adaptive structure. We look forward to having further collaboration with you on IEEE platform in the days to come. I would also like to announce that in the month of September, we'll be having an additional talk. Usually we have the webinar series only on the 2nd and the 4th Wednesday of every month. But this month, we are also having a Selvarajan Memorial talk, which is in memory of Professor Selvarajan, who was instrumental in the founding, he was in the founding members of IEEE. The talk will be delivered by Professor Ravindra Dahiya, Director of Electronic System Design Center, Department of Electronics and Nano Engineering, University of Glasgow. This talk will be on September 19th at 5:30 p.m. Indian time. And the title of the talk is Electronic Skin with Distributed Sensors and Computing. I request all the audience to make yourself available and make it convenient to attend this talk and benefit from him. Also, we'll be continuing with our webinar series every 2nd and 4th Wednesday of the month. I once again thank the speaker and all the audience for this wonderful interaction and making this a success. Thank you so much, madam.
Thank
you,
you.
everyone.
Yeah. Thank you, Mary. Have a good day.